So last video we left off with some formulas. And again, just keep a sheet of paper with these on them, especially the ones for the basic functions like power functions. This formula right here that I'm highlighting covers all kinds of functions. It covers the constant function. Just let a be 0 and n be 0. So the function 1, if a is 0 and n is 0, you get 1 over s. It covers all powers of t, positive integer powers of t, by letting a be 0. And it covers all exponentials by letting n be 0. Then this covers the sign, and sign times any exponential, because remember, multiplying by an exponential before computing a Laplace transform just means shifting the Laplace transform. So instead of s, you have s minus a. Same thing for cosine. In general, we have this formula, power times any function, so we could do powers times trig functions here using this. You just have to differentiate. You just have to differentiate and apply this formula. Formula 5 here is we talked about was kind of reverses 4. It's kind of a backwards version of 4. I've never really needed to use it, but it does exist. And we're going to use equation 6 here. But we're going to use it to derive a formula, and once we have that formula, we're not going to really need to do it again. But you do need to know how to use it for problems in the book that aren't the specific kind that we're going to deal with in homework. So practicing this stuff in your book, you're going to get first-order equations to practice with. I highly recommend doing the first-order equations in your book because they don't involve as much work, and you can get through more of them. But it still forces you to learn how to do the steps that are involved. And when we get to the second-order equations, we'll have basically we're going to derive a formula for how to solve it. And all you're going to have to do is plug in your given information, determine one Laplace transform of the right side of the equation, and then plug everything in, and you'll get that your solution is some inverse Laplace transform of some horrible function. And you're just going to break that horrible function into pieces that are simpler to work with, and then use a table or some formulas to compute the inverse Laplace transforms, and then you have your answer. So another formula we're going to need, which arises from time to time, is called convolution. Convolution is a procedure where you take two functions to create a third function. And there are a whole bunch of different kinds of convolution in different areas of mathematics. It's a very general thing. It's a general idea which for specific applications looks different, but it's doing some general thing that's the same. All right, it's kind of an averaging operation. You're not exactly computing an average, but from a mathematical point of view, that's what it is. It's kind of looking at the average distribution of two functions together, combined in some way. So here's just what the definition is. You give me two functions f and g, and you give me a number t. I multiply f of t minus z times g of z, and then I integrate that in z from 0 to t. So every t is going to give me a different value, so this is a function of t. The important formula we're going to talk about right now is that if you have a function which is a convolution, and you apply the Laplace transform to that, it's really easy to compute that. All you have to do is compute the Laplace transform of f, and then the Laplace transform of g, and then those two functions you just multiply together. Now we're hardly ever going to do that, but we will use the other version of this equation, which is the same equation, just written differently, is that the inverse Laplace transform of a product of two functions is just the convolution of the two inverse Laplace transforms. That's the one we will use. So we're going to prove the first one here, but then realize that it's the same as the second one. They're logically equivalent to each other. It's the same formula. So, but the second one is the one we're going to use. So I'm just writing down what the definition of these symbols are. The Laplace transform of a convolution. Laplace transform is integrate from 0 to infinity, e to the negative st, some function of t. The function of t I'm plugging in here is the convolution of f and g, or f star g. Now, this next step is a key observation to make this work is, what are we doing? We have to pay attention to order of operations. dt is on the outside, which means the 0 to infinity integral is referring to t, not z. The 0 to t is referring to the integration in z. So what are we doing? We're integrating a function of two variables, really. And we're restricting our variables to t ranging from 0 to infinity. And for each of those t's, z is only ranging from 0 to t. So in the end, we're considering all possible values of, all positive values of z and t, but z is always less than t. Well, that's the same thing as saying, let's consider all positive values of z and t, but t is bigger than z. So that what that does is, by taking that equivalent point of view, we can just change the order of our integration, because integrating is just adding. So adding is commutative. And for integrals, it doesn't always work, but for the ones we run into, it will. By changing that point of view, we're allowed to switch the order of integration. So I integrate in t first, but t is bigger than z, so it ranges from z to infinity. And then for each of those t's, I'm considering all z's, or I should say, for each z from 0 to infinity, I'm considering all t's that are bigger than z. That's the same thing as, for each t that's bigger than 0, consider all z's less than t in the first integral here. So these two are the same thing. They just look different, and it's easier to work with. Now the stuff in parentheses looks almost like a Laplace transform of f, except there's a minus z there, and there's a z in the limit of integration. Let's do a substitution. Let's replace t minus z with u, or y. I'm going to use y in this case. We'll let y equal t minus z, where t is our variable. Z is a fixed number. So if y equals t minus z, then dy equals dt, because z is a constant. Derivative is 0. So dt is going to become dy. This t minus z is going to become y. And this t up here, and the exponential, is going to become y plus z. Just think about it. If y is t minus z, then t is y plus z. And then the last thing we change is the limits of integration. If y equals t minus z, then when t is 0, when t is z, y is 0. And when t is infinity, y is infinity. So the substitution just makes our expression now look like this. And now we've got two integrals where they're both from 0 to infinity. And we've actually separated the functions. We've got an e to the negative sy and an e to the negative sz, because properties of exponentials lets us split that up. So we can factor that e to the negative sz out, because it doesn't depend on y. So all the y stuff is in the y integral, and then all the z stuff's in the z integral, and they're basically separate now. We can compute them separately. But the stuff in parentheses now is just the Laplace transform of f, evaluated at the input s. That's a number that doesn't depend on z, so it factors out. Once we get rid of that, what do we have? We have the integral from 0 to infinity of this stuff, which is just the Laplace transform of g. And that's justifying the formula. All right, but again, the more important one is the inverse formula. Is the Laplace transform of a product of two Laplace transforms is just the convolution of the two inverse Laplace transforms. So let's look at an example of how you actually do this. So let's just pretend that we've applied the Laplace transform method to solve a differential equation, and after doing basically plugging things in and doing some algebra, we identify that whatever our solution x of t is, it's the inverse Laplace transform of all this junk. So that's a horribly complicated looking thing, and you're not going to find everything in a table, but you'll find simple things in a table. So you want to split this up and break it up into pieces that are simple. So keep in mind, and I just did this Okay. Keep in mind that the inverse Laplace transform, just like the Laplace transform, is a linear operator. So I can split up sums in the numerator. All right. So this is really two terms written as one. It's 1 over the denominator plus s squared over the denominator. So I can split that up. And once I do that, notice that the s squared term cancels. You get s squareds canceling. So that's the second term we see here now. Simplifies. And that's a simple thing that we know from a formula or a table. All right, that's that 1 over s squared plus 3. That is our Laplace transform of the sine or cosine. I don't always remember. I have to look it up. But it's one of those. And then what do we have in the first term? The 1 over s squared times s squared plus 3 is really a product of two things. Notice remember what we just got done doing. We proved a formula. The inverse Laplace transform of a product can be computed by convolving the inverse Laplace transforms of the two things that are creating the product. So all I need to know is what's the inverse Laplace transform of 1 over s squared? That's t from our power function formula. And what's the inverse Laplace transform of 1 over s squared plus 3? Well, again, it's a sine or cosine. I forget. I got to look it up. So the second term, and I looked it up, it's a sine. So this 1 over s squared plus 3, the inverse Laplace transform of that is sine of 3t. So now what do I have to do? I have to compute the convolution for this first term, the convolution of the function t with the function sine of 3t. So I integrate from 0 to t. I plug t minus z into t, and I plug z into sine of 3t. It's just the definition of the convolution. Now this is two integrals split by a minus sign. T is a fixed number. So the first integral is just computing an integral of sine of 3z. That's easy. The second integral is computing z sine of 3z with a minus sign in front. You can do that with integration by parts. Okay, I'm not going to go through all those details, but you do that, and in the end, what you end up with is this. So if you applied Laplace transform method to a differential equation and determined that your solution was the inverse Laplace transform of this stuff, then we just figured out what x is. It has to be this. All right, that's just one example of how to do this, but it covers all the kind of bases. You need to be able to look up inverse Laplace transforms of very simple functions, and you need to realize that when you compute the inverse Laplace transform of a product of two things, that it turns into this convolution corresponding to the convolution of the inverse Laplace transforms of the two things that are forming the product.